Almost everything we are told to do about energy runs through one small object, the battery. Electric cars, phones, laptops, and the giant banks that store power from the sun and the wind. Nearly all of them lean on the same chemistry: lithium. Lithium is genuinely good at its job. It is light, and it packs a lot of energy into very little weight. But it has a quiet problem. There is not very much of it, and what there is sits in only a handful of places on Earth. So the price swings, the supply is fragile, and the whole clean energy transition ends up balanced on a metal that is scarce. The obvious question is the one almost nobody could answer for years. What if we could build a battery out of something we will never run out of? Here is the idea that just made one of the world's most respected technology lists. Build the battery out of sodium. Sodium is 1/2 of ordinary table salt. It is in the sea. It is in the ground as soda ash. Measured against lithium, it is about 1,000 times more abundant, and it is spread all over the planet instead of locked in a few countries. Think about that gap. One element you have to dig out of a few mines, against another you could pull straight from the ocean. That is why sodium-ion batteries were named one of MIT Technology Review's 10 breakthrough technologies of 2026. Not because they beat lithium at everything. They do not. But because they trade a little performance for something strategic. A battery you can make, almost anywhere, from material that is cheap and effectively endless. To see why sodium can stand in, you need one simple picture of what a battery is. A rechargeable battery is basically a rocking chair for charged particles. There are 2 sides, 2 electrodes, with a liquid called the electrolyte in between. When you charge it, you push ions across to one side and store them there. When you use it, those ions roll back across to the other side, and that flow drives electrons the long way around, through your motor or your phone. That electron traffic is the electricity. A lithium battery rocks lithium ions back and forth. A sodium battery does the exact same dance, with sodium ions instead. Same chair, different passenger. And once you see it that way, the real engineering question becomes clear. Can the bigger, heavier passenger ride comfortably in the same kind of seat? This is where honesty matters, because sodium is not a free win. A sodium ion is larger than a lithium ion, and it weighs more than 3 times as much. In a battery, bigger and heavier passengers mean you store less energy for every kilogram and every liter of cell. In real numbers, today's sodium-ion cells hold roughly 140 to 160 watt-hours per kilogram, with the newest reaching about 175. That is in the same neighborhood as the cheap, safe lithium iron phosphate batteries, but well below the high-energy lithium cells in a long-range car. There is a second cost, too. Because the sodium ion is bigger, the cell is bulkier for the same energy, and for a phone or a sports car, that's space. For decades, that gap is exactly why sodium was set aside. Lithium won the race for energy density, and sodium waited on the bench. So what changed? Engineers had to redesign the 2 electrodes around sodium's size, and the first problem was the negative side, the anode. In a lithium battery, the anode is graphite, neat stacked sheets of carbon, and lithium slips quietly between them. Sodium does not. It refuses to settle into graphite in any stable way. For a long time, that single fact looked like a dead end. The answer was to stop using neat carbon and start using messy carbon. It is called hard carbon, a disordered, jumbled form full of tiny pores and gaps. Where graphite is a tidy library of shelves, hard carbon is more like a sponge, and sodium is happy to sit inside its holes. That one material, hard carbon, is the workhorse anode that made modern sodium-ion batteries possible. The other side, the cathode, brought a bonus. Sodium-ion cathodes come in a few flavors, with names like layered oxides, Prussian blue analogues, and polyanionic compounds. The details matter less than one shared feature. Many of them are built from cheap, abundant metals like iron and manganese, and they need no cobalt and no nickel. That is a bigger deal than it sounds. Cobalt and nickel are among the most expensive and most ethically troubled materials in a lithium battery. Designing them out does not just cut cost. It cuts a whole tangle of mining, geopolitics, and supply risk out of the cell entirely. Then there is a quieter trick that saves money on its own. Inside a lithium battery, the anode has to be wrapped around a sheet of copper because lithium reacts with aluminum at low voltage. Copper is heavy and not cheap. Sodium does not have that problem. It leaves aluminum alone. So a sodium-ion cell can use light, cheap aluminum on both sides instead of copper. And there is a safety dividend. Because of how it is built, a sodium cell can be run all the way down to 0 volts without ruining it. That means it can be shipped and stored completely empty, with no stored charge waiting to go wrong. A battery you can transport at 0% is a much safer battery to move around the world. Put those choices together, and you get a cell with a different personality. Sodium-ion batteries tend to shrug off being overdrained, and they are less prone to the runaway overheating that makes lithium fires so dangerous. It is the kind of battery you can stack by the thousand in a warehouse and not lie awake worrying about it. They also handle cold far better. Some sodium cells keep more than 90% of their capacity in deep, freezing temperatures that would leave a lithium battery gasping. And the headline number, the one that put this on every analyst's desk, is cost. By leaning on abundant materials, sodium-ion could cut battery cost by up to about 30%. Cheaper, safer, cold-tolerant. For a lot of jobs, that is a better trade than squeezing out the last watt-hour. So let us be clear about where this actually fits, because the hype can run ahead of the truth. Sodium-ion is heavier and less energy-dense, so it is not going to power a flagship phone or a long-range luxury car anytime soon. Those stay on lithium. But think about everything that does not need to be light. The giant battery farms that store solar power for the grid, backup power for data centers, cheap city cars, and the oceans of electric 2- and 3-wheelers across Asia. Stationary storage alone is a market measured in the trillions of dollars over the coming decades, and almost none of it cares how heavy the battery is. For all of those, weight barely matters, but cost, safety, and a supply you can count on matter enormously. That is the exact shape of the sodium-ion sweet spot. And this is not a someday story. It is shipping. In 2025, the world's largest battery maker, CATL, launched a sodium-ion brand called Naxtra and started making it at scale. In early 2026, CATL and the carmaker Changan revealed the first mass-production passenger car running on those sodium cells, headed for the market by the middle of the year. Other companies, from BYD to Natron Energy in the United States, are pushing sodium cells into grids, factories, and data centers right now. In the United Kingdom, Faradion, now owned by Reliance, is carrying the same chemistry toward India's enormous demand. The lab phase is over. The factory phase has begun. Step back, and the real breakthrough is not a single number on a spec sheet. It is what sodium changes about the whole system. For the first time, the cheapest, safest layer of our energy storage does not have to depend on a scarce metal pulled from a few corners of the world. It can be made nearly anywhere from salt. So here is the shift worth remembering. The future of energy was supposed to be a race for the most powerful battery. Sodium-ion is a reminder that sometimes the breakthrough is not the strongest option. It is the one we can build enough of. This is Paperscape. The sources are linked below. See you in the next one.